super basic physics. It's just Alice at rest in air, while drifting through, and everything very, very simple physics. Okay, so, and then what we did is, we said, okay, well, let's try to figure out what this K is, because that's the really important thing. If we know what that K is, then we know how much time lapses for Bob, when it's time lapses for Alice. One way to determine K is to simply assume. Simply assume that when 1 second lapses for Alice, 1 second lapses for Bob, and 1 second lapses for everyone in the universe, there's such a thing as absolute or universal time. And 1 second lapses for one person, 1 second lapses for anyone regardless of their state of motion. In which case we just said, oh, well, that means that this time here, D plus ct must equal that, kct, and then we solve for K. And then we found that, in fact, K is just the ordinary Doppler shift for sound in air. Okay? And what we're going to do now is we're going to drop that assumption about universal time and find a different way of calculating K, a more natural way of calculating K. And we'll find that K is not what we got before, something different. And it tells us that the amount of time elapsed for Bob from here to here is not the same as the amount of time elapsed for Alice from here to here. Universal time does not exist. And time is different for everybody. Everybody has their own sense of time. Okay, so that's the goal here. Okay, so to reach that goal, what we're going to do is we're going to take this picture here, which works for sound in air, and we're going to imagine that instead of Alice and Bob exchanging sound signals in air at rest, we're going to imagine that they're exchanging light signals. Okay, so the speed of sound is going to become the speed of light, and subsonic is going to become subluminal and all that stuff. So we're just replacing sound with light. Okay, so the first step here is just so that we have a concrete picture of what's going on, and to make the picture as close as possible to what we had for sound. What we're going to do is we're going to imagine that light is a wave in ether. Some of you know about the concept of ether, heard about the concept. How many of you not heard ether before? The word ether. Okay, so about a third of you. Okay, so it turns out that in the early 1800s there were experiments done which showed that light is a wave phenomenon. Okay, and so it exhibits wave properties like diffraction, interference, that kind of stuff. So everyone thought, yeah, okay, light is a wave, great, fantastic. Okay, so then they looked at other waves. They looked at water waves, and they goes, what is a water wave? A water wave is a disturbance of some medium. Okay, so the water molecules, when you really splash in the water molecules are going up and down like this. Okay, so there's something waving. In the case of water waves, it's the water molecules that are waving. Okay, they also knew that sound is just vibrations of some other medium in air. Okay, so when you talk and sound comes out, it just means that air molecules are vibrating up and down. Okay, so the air molecules are waving back and forth. So then they thought, well, okay, light is a wave. So what's waving? Okay, and they thought, what's waving? Well, I don't know, can't really see anything waving. Okay, and so they invented this medium called the ether. And they imagined that the ether is the sort of elastic medium like air or like water that pervades all of the universe, fills all of space. And that light is just a wave in this ether. So when I click on a flashlight, what it does is, imagine this ether is like jelly. Okay, cool, jelly covers the whole universe. I jiggle the jelly over here, then it will jiggle neighboring jelly, which will jiggle neighboring jelly, and so on, like dominoes, you get a wave going out. So they imagine that light is a waving of this sort of elastic medium they call the ether. Okay, so let's go with that model of light. Okay, so that model of light was actually what was used for all of the 1800s until the beginning of the 1900s. Okay, so let's suppose that light is a wave in ether for a moment. I'll put a question mark there, because it actually will show that it's not that. So light is a wave in ether, and that's exactly analogous to sound being a wave in air. Okay, so what we're doing is we're going to take this picture here, and in the backdrop of this picture we have in mind still air. So now in the backdrop of this picture we're going to have in mind ether. Okay, and Alice rests with respect to this mysterious medium called the ether. And she is, instead of clapping her hands sending a sound signal, she's sending light signals. The point is that this situation here, light as a wave in ether, is completely analogous, 100% the same as sound as a wave in air. So we can take this diagram and use exactly the same thing, draw exactly the same picture for an experiment in which Bob is drifting through her frame, Alice waits on T, clicks on her laser, and sends that laser right over here, and Bob has a mirror which reflects that laser like that. And the important thing is when he reflects it back, the speed of light is independent of the motion of the source. So in this case, Bob is drifting through that mysterious ether medium. But when he clicks on his flashlight or laser or sends it back to the mirror, that light travels with respect to the still ether, or the speed c, which is now the speed of light. And so Alice will measure that speed to be c independent of the motion of Bob, depending on how fast he's moving under a layer toward her. So this becomes c becomes the speed of light. And this becomes Bob is moving, that's something like subluminal. Okay, something moving superluminal would be like that. Faster than the speed of light. Okay, so that's our picture. We just carry over in its entirety without any change. Okay, so Einstein, let's now switch to the possibility of Einstein and then theory of special relativity. So Einstein based his theory of special relativity on two principles. And one of those principles has to do with the speed of light. Anyone tell me what that principle states? Yeah.
Speed of light. You say that speed of light is the same as the speed of light. Okay,
yeah, so that's the general consensus of what Einstein said, is that somehow the speed of light is the universal constant, the same for everybody, the same in any reference frame, the same blah blah blah. That's actually not what Einstein said. Okay, so this is a very important point that I want to make here. What Einstein actually said was this. Okay, so there are two principles, principle 1 and 2. We'll start with principle 2, which is the speed of light principle. Okay, so understanding this principle properly will really help you understand the logic of special relativity, why it makes sense, why it's totally believable, why it's the most natural thing you can imagine, or the most natural way the universe could be. Okay, so let me actually read what Einstein said. And before I read that, I have to, before I read the principle, I need to read what he said a little bit earlier to find some terminology. Okay, so this is something of my favorite special relativity. He says, well, let us take a system of coordinates in which the equations of Newtonian mechanics hold good. In order to render our presentation more precise, and to distinguish this system of coordinates verbally from others, which will be introduced hereafter, we call it the stationary system. Okay, so what he's introducing is a reference frame, a coordinate system. Okay, so Alice is some state of motion, okay, and such that the laws of Newtonian mechanics hold good, which means F equals ma and all that kind of stuff. Okay, so when you throw something like this, and there's no forces acting on it, it moves in a straight line, all that kind of stuff. So he's saying, suppose there exists such a frame. Okay, we will call, and then we're going to do all kinds of stuff with that frame, but suppose there exists such a frame, let's call that frame the stationary frame. And then he states his principle, the principle of the constant velocity of light, which reads, any ray of light moves in the stationary system of coordinates with the determined velocity c, whether the ray be emitted by a stationary or by a moving body. Okay, so let me just paraphrase that. So combining what I just said, I'm going to write it, write it this way. And we'll talk about it. we know that there's no such thing as absolute rest. That's one of the ideas that we can anticipate what's coming. We know there's no such thing as absolute rest. There's no such thing as absolute space. All that, that's what we're going to get to. Okay, so when we say observer at rest, we put in quotation marks indicating that really what we need is what Einstein is saying here. There exists at least one frame of reference in which it is true that Newtonian mechanics holds good. Okay, if I throw an object and it's opposed to acting on able to move in a straight line, there exists at least one frame in which that's the case. So this is the frame that Einstein calls the stationary frame. Okay, so I'll just say this thing. So there exists. There exists at least one frame in which this is true. In which the speed of light is c independent of the motion of the source. Okay, so at the time, this is 1905, people had in mind that most physicists thought that light is a wave in ether. Okay, so is this principle true for a light is a wave in ether? What? So sound wave. Exactly the same as the sound wave in still air. Okay, so sound waves moving around still air. If you're at rest with the air, doesn't matter how the source is moving around, if the matter is coming toward you or moving away from you, the speed of sound will be the same. You will be opposite in turn when it's coming toward you. The frequency goes up, when it's moving away from you, the frequency is lower. But the sound, the speed of that sound wave is always c with respect to still air. If you're at rest with still air, you will always move at 16 c. Okay, and if light is a wave in ether, it's exactly the same thing applies. Okay, so this principle is obviously true if light is a wave in ether. It's not a phenomenon. Okay, so what I want to, okay, yeah. Okay, so let's leave it at that. So what I want to emphasize here is that this principle, it would have been completely obvious to anyone in 1905. Okay, this isn't anything surprising or something radical about this principle. Everyone would have read that and said, yeah, okay, that's obvious, so what? Okay, so let me just emphasize, it's very important. Let me see why it's obvious. Okay, so there's a whole bunch of reasons why it's obvious. One is this. The people at the time had in mind a particular model of light. Okay, they didn't actually know, well, this is what they thought light is. The fact is we still don't know what light is exactly. Okay, we don't, you think of string theory, okay, light is equal to string and so on and so forth. Okay, we still don't actually know what light is at a really fundamental level. We understand light a lot better now than we did back then, but we still really don't know what it is. But anyways, so at that time, people had this wave and ether model, this mechanical model of light. That light is this mechanical phenomenon. That's a physical vibration of some medium called the ether. Just like sound is a mechanical phenomenon, it's a vibration of some physical medium. So that's a mechanical wave and ether model. The wave and ether model of light just like sound and predict that this is true. And so everyone said, yeah, that's obvious. Way to go, Einstein. The second reason is people were aware also that light is an electromagnetic phenomenon. So Maxwell in the 1860s had come up with Maxwell's equations, which describe how electric and magnetic fields are unified, are just different sides of the same coin. How they work together, one oscillates and then the other oscillates, so how they work together to produce an electromagnetic wave, which moves through space and carries energy and all that kind of stuff. And it was known that light is an example of an electromagnetic phenomenon. So light is electromagnetic waves of a certain wavelength or a certain frequency range. And so the second thing people would have known at the time is that Maxwell's equations, which describe light, which are the mathematical embodiment of how light behaves, Maxwell's equations also predict this. Okay, so I should elaborate a little bit on that. So what Maxwell's equations say, okay, so what Maxwell's equations say is that, at least classically, not exactly, classically, the source of all light is accelerated electric charge. Okay, so what does that mean? So that means if I take a charge like this, a charge at rest will not emit light. A charge in uniform motion will not emit light. But a charge that's accelerated, if I take that charge and jiggle it back and forth, then it will emit electromagnetic waves, which is a form of light. Okay? Right, so let me put it this way. Suppose that you are out in space, floating out in space on some platform here, and you see some charge out here, and this charge is moving around in some figure random way, like this. What's going to happen is that charge, which is accelerating, okay, it's changing its velocity, is going to be emitting electromagnetic waves. And those waves will come at you, and independent of the motion of this thing, it's accelerating, it's going to emit electromagnetic waves, and you will see the speed of those waves that you see. Okay, if I were to take this same charge, this charge is wiggling around here, and I were to give it an extra drift, okay, to the right, for example, or to the left, okay, so take this whole pattern of jiggling around and add sort of a drift to the right. Okay, well, that's the equation would say, it's still just a charge wiggling around, independent of the motion of that source, the speed of the waves you can measure and see. Okay, so everyone would look at that and say, okay, yeah, that's right, Albert. And also, there would have been experimental evidence available at this time through astronomical observations. Okay, so it turns out that, sorry I might get into this, but it turns out that there's very, very simple observations that you can make of binary star systems. So most of the majority of stars in the galaxy are actually binary pairs. So two stars orbiting around each other. There's plenty of examples of this. And if you look at the telescope, you will, and you study the motion of these guys, you will also conclude that the speed of light is independent of the motion of the source in that case being either star. And so at one time the star is moving towards you, and at other time it's moving away from you, and so on. Simple observations that I might get into give you strong experimental evidence that the speed of light is independent of the motion of the source. Okay, so everyone would have believed this, everyone would have said, yeah, totally obvious. I want you to compare this statement that I wrote down here with a seemingly, with a closely related statement, but a totally different statement, and that is, that's called T2 prime. Okay, so this is what Einstein did not say. Okay, if we were to take this statement and we were to replace the word observer here with source, and replace the word source with observer, we'll just interchange those two words. Okay, so it's exactly the same statement for a source at rest. The speed of light is c independent of the motion of the observer. Okay. So that seems like a simple switch around, right? No big deal. But if we think about it for a minute, it is a big deal. This is a totally bizarre statement. Okay, so for a source at rest, the speed of light is c independent of the motion of the observer. So that's like saying, suppose I have a flashlight here, that is at rest, it's a source of light which is shining a beam this way, and it would be telling me that the speed of light is independent of the motion of the observer. Okay, so suppose we've got this beam of light coming toward me, I'm at rest with respect to that source, that flashlight. So how do I measure the speed of light? Well, what I do is I take a meter stick like this, I time how long it takes a light wave front to cross from one end of the stick to the other end, I time how long it it takes, and I divide and I get the speed of light. Okay? And I would find, 3 times 10 theta, whatever. Now this is saying that I would get the same value of the speed of light even if I were running towards that light, which is completely bizarre. I mean, light is a wave in ether. Okay? It's moving at some speed, c, with respect to that still ether. If I now start moving with respect to that ether, moving toward that light, with a speed d, what speed should I measure? The speed of light. C plus d. If I'm running away from the flashlight, what speed am I going to measure? C minus c, right? So what if light instead is particles? So if we have particles coming out of this flashlight with some speed c, particularly empty space. Okay, so if I'm at reference to the flashlight, I see the moving particles with speed c. If I'm running towards those particles with speed d, I'm going to measure running away. Okay, so it's totally bizarre, right? So this statement makes no sense. This statement is completely unbelievable. And so just wanted to point that out. Okay, so this is totally bizarre. Keep going totally bizarre. Okay, so at the end of the day, what we're going to show is that T2 prime actually follows from this and the relativity principle. And the goal of special relativity was to try to understand, because this isn't that true. Okay, but it's not obvious how it could possibly be true. And the goal of special relativity is to understand why this is true. Okay, so that's what we're going to get to. Alright, so in order to get there, we need Einstein's second principle, which is the more important principle, which is the relativity principle. Okay, so sorry, Albert. And also, there would have been experimental evidence available at this time through astronomical observations. Okay, so it turns out that, so I might get into this, but it turns out that there's very, very simple observations that you can make of binary star systems. So most, the majority of stars in the galaxy are actually binary pairs. So two stars orbiting around each other. There's plenty of examples of this. And if you look at the telescope, you will, and you study the motion of these guys, you will also conclude that the speed of light is independent of the motion of the source. The source in that case being either star. And so at one time the star is moving toward you, and another time it's moving away from you. So simple observations that I might get into give you strong experimental evidence that the speed of light is independent of the motion of the source. Okay, so everyone would have believed this. Everyone would have said, yeah, totally obvious. I want you to compare this statement that I wrote down here with a seemingly with a closely related statement, a totally different statement, and that is that's called the T2 prime. Okay, so this is what Einstein did not say. Okay, if we were to take this statement and we were to replace the word observer here with source, and replace the word source with observer, so just interchange those two words. Okay, so it's exactly the same statement for a source at rest. The speed of light is c, independent of the motion of the observer. Okay. So that seems like a simple switch around, right? No big deal. But if we think about it for a minute, it's a big deal. This is a totally bizarre statement. Okay, so for a source at rest, the speed of light is c independent of the motion of the observer. So that's like saying, suppose I have a flashlight here that is at rest. It's a source of light which is shining a beam this way, and it would be telling me that the speed of light is independent of the motion of the observer. Okay, so suppose we've got this beam of light coming toward me and I'm at rest with respect to that source, that flashlight. So how do I measure the speed of light? Well, what I do is I take a meter stick like this. I find how long it takes a light waveform to cross from one end of the stick to the other end. I find how long it takes, and I divide, I get the speed of light. Okay? And I would find, 3 times 10 theta, whatever. Now this is saying that I would get the same value of the speed of light even if I were running towards that light, which is completely bizarre. I mean, light is a wave in ether. Okay, it's moving at some speed, c, with respect to that still ether. If I now start moving with respect to that ether, moving toward that light, with a speed d, what speed should I measure? The speed of light. C plus d. If I'm running away from the flashlight, what speed am I going to measure? C minus d, right? So what if light instead is particles? Suppose we have particles coming out of this flashlight with some speed c, drifting through empty space. Okay, so if I'm at reference to the flashlight, I see the moving particles with speed c. If I'm running toward those particles with speed d, I'm going to measure. I'm running away. Okay, so it's totally bizarre, right? So this statement makes no sense. This statement is completely unbelievable. Okay, so just wanted to point that out. Okay, so this is totally bizarre. Keep going, totally bizarre. Okay, so at the end of the day, what we're going to show is that T2 prime actually follows from this and the relativity principle. And the goal of special relativity was to try to understand, because this isn't that true. Okay, but it's not obvious how it could possibly be true. And the goal of special relativity is to understand why this is true. Okay, so that's what we're going to get to. Alright, so in order to get there, we need Einstein's second principle, which is the more important principle, which is the relativity principle. Okay, so let's start over here. So we'll call this principle number 1. This is the more important of the two principles, and that's the relativity principle. Okay, so I'll just write out a paragraph. I'll read it now, and then we'll paraphrase it, and we'll talk about it. Okay, so principle of relativity according to Einstein is that the laws by which the states of physical systems undergo change are not affected whether these changes of state be referred to one or the other of two systems of coordinates in uniform translatory motion. Okay, so let's paraphrase that to read this. With any two inertial observers in uniform relative motion. Both are equally entitled to consider themselves to be at rest. Okay? So, so let me just read the whole thing. So given any two inertial observers in uniform relative motion, both are equally entitled to consider themselves to be at rest. Okay, so the word inertial here, the word inertial means that the observers are not experiencing any acceleration. Okay, so they're floating through empty space, and they have their jetpacks or their rocket engines or whatever off, turn them off. So they're not accelerating anyway. So it's just not accelerating or rotating relative to the distant stars. Okay, that's a very deep statement there, but we won't actually fall into that black hole. Okay, so not accelerating or rotating and they are in uniform relative motion. So what Einstein has in mind here is there's two observers floating out in the middle of empty space, just drifting there, and in some state of motion. And when one looks at the other, they say, you're going, say, that way with the speed d, or this one looks at that one and says, no, you're going that way with the speed d minus d. Okay? So they're sort of drifting apart or toward each other, whatever, some uniform relative motion. Both are equally entitled to consider themselves to be at rest. And at rest here is putting quotation marks, meaning the same sort of thing as at rest over here. Okay, so we're going to tie these two together with that word, with that phrase at rest. Okay, so let me give you an example of this. So suppose that you are in a train car, and this train car has all the shades down, and the train car is at rest on the tracks. And you're inside, so you're just basically inside a room. Okay, and there's a pool table there. Game of billiards, maybe play pool billiards. Okay, so basically all of you, okay. So what you're doing, you have a stick, and you're shooting the cue ball around and so on, and you're observing the way these balls behave. Okay, so you observe certain things. You observe stuff like this. So here is one of the banks of the table here. You observe that when you shoot a ball like this toward the bank, if it's spinning to the bank at 45 degrees, it's going to bounce off like this. What's the angle there? 45. Okay. What if you put a spin on it? So if you spin it this way, and you hit the bank, this angle will be less than or greater than 45. Less. Good. Okay, so and suppose that you have a ball like this, and you pitch another ball like this, and a bang like this, so one goes that way and one goes that way. What can you tell me about this physical phenomenon? Momentum is conserved, right? So you add up the initial momentum, and you find that that's equal to the sum of the final momentum of the ball conserved, right? So you observe the behavior of these balls reflecting off the sides, equal angles, and all that kind of stuff. And if one ball is spinning one way, you hit a ball at rest, it will transfer on this spin and everything. So you learn all about the behavior of these balls. Okay? And then after a hard day of playing pool, you go to sleep, you wake up the next morning, and you're at it again, you're playing pool, and you shoot the balls around, stuff like that. And unbeknownst to you, in the middle of the night, the train, while you're sleeping, the train is taken off. Okay, and now it's looking down the track at like 100 kilometers per hour or something. And the advance of the track is very smooth and perfectly straight. Okay, and there's basically no vibration, so it's like a maglev train or something, that's super smooth. Okay, so you can't feel any vibration, you can't hear the engines going, whatever. The shades are gone, so you can't see trees looking by you and so on. And so you just wake up in the morning, and whatever. You were saying before, you play the game of billiards, you shoot a ball like this, you say, oh yes, that angle, that angle. And when I shoot one ball to the other, I observe yes, conservation of momentum and all that kind of stuff. And so you observe that the game of billiards plays out exactly the same as it did the previous day. Okay? So the point here is that the velocity of the train on day one was at rest with respect to the tracks. On day two, it's moving with respect to the tracks. The velocity of that train with respect to the tracks has no effect on the way that these balls behave. In other words, there's no way, by making observations about how the balls behave, that you could get any information about how fast you're going. Okay? That's a very important point. That's basically what this principle of relativity is saying. So let me say it this way. So no way to determine velocity okay, so I'll just say it again slightly differently. What it's saying is that the unaccelerated motion of a system, of a room, has no effect whatsoever on the way things behave, the way things happen in that room. That's what it means. Okay, so let's talk about whether this principle is, or this idea, this principle, T1 here, is believable or not. Okay, well, first of all, it's obvious. It's certainly not to apply, it's completely obvious to anyone if you apply this principle to mechanical phenomena. Balls, like cars, like whatever. It was totally obvious for mechanical phenomena, even all the way back to Galileo. So even Galileo knew this. Newton certainly knew this very well. Everyone knows this. Okay, but it's not so obvious for electromagnetic phenomena.